Hi. So we've now seen an implementation of scheduling that retains precise state. We saw the design of the MIPS R10K pipeline. It introduced some new structures, such as the physical register file and the reorder buffer that, relative to Tomasulo's algorithm, the major change was a shift to a big register file where register tags now point to a physical register rather than a reservation station entry. We also saw the reorder buffer in action, which tracked both the old and new tags for every instruction's output register so that we can restore precise state if we need to. In spite of these changes, we saw some familiar characters. The reservation stations are still a key part of the dispatch and issue stage, but now the fields only track the tags of input and output registers, no more values in the reservation stations. And similarly, the map table was another familiar face in its design. In this video, we bring that implementation to life through an example of the MIPS R10K processing some code, just as we did with our investigation of Tomasulo's algorithm. The purpose of this example is to understand how these structures are used in the R10K. So despite all the support to support precise state, we'll defer to a later video to see how recovery is actually implemented. In this video, everything will go right. No misspeculations and no exceptions. So before I dive in cycle by cycle, let's get a quick tour of the structures that we'll be tracking in detail in this example. In the upper left is a combined reorder buffer and instruction status table, where we see the old and new tags for an instruction that is allocated an entry here. We'll be tracking the head and tail pointers, H and T over here, which represent the earliest active instruction in the instruction window, as well as the most recently dispatched instruction. We'll see that the ROB is a circular buffer, and that when the tail pointer is just above the head pointer, dispatch must stall. We've run out of allocatable space. Just as with the Tomasulo example, we'll also fill out the cycles at which every instruction dispatches, issues, executes, and completes. The latter stage is new here in dynamic scheduling with speculation, and I've hidden the fetch and retire stages. Note that we need to track the status of every instruction in addition to the old and new tags, either in the ROB or in a separate instruction status table, so that we can know when can we retire the head instruction and deallocate crucial on-chip resources. And on the other side of the buffer, when does the dispatch stage need to stall? So we need to track what state every instruction in our instruction window is in. As with our Tomasulo examples, the reservation stations are specialized to a particular functional unit, an adder, a multiply, and load store reservation stations. The units are not shown, nor is the load store queue. There's also a branch reservation station not shown. Now the map table is quite similar to what we saw in Tomasulo's algorithm with some key differences. First, registered tags now point to physical register IDs, and therefore these fields can never be empty. So we start out in an initial state where every register name is mapped to some physical register. So these are never empty. And we also have this new ready bit, the plus symbol there, which indicates whether the instruction that will write to this register name has actually finished its execution, whether it has completed. When an instruction dispatches that actually has an output register, we'll need to update the map table, requiring some entry from the free list over here. We have 8 total physical registers available in our physical register file, and we have 4 registers initially available to be allocated. Another interesting change is that the common data bus only broadcasts the tag when an instruction reaches the complete stage. And that is, as we saw in the last video, because no values exist anywhere in the processor except in the physical register file. When an instruction reaches the complete stage, it writes to its output physical register directly. There's no need to broadcast the value to the map table, to the reservation stations. So those are the structures, and last but not least, a reminder of the code that we're executing here. It's the same program, single precision A times X, from the Tomasulo examples, where we have 3 read after write dependencies on F0, F4, and R1. These are the tight read after write dependencies. And of course, the load and store also depend on updated values of R1. So those dependencies are what will possibly result in instructions waiting in the issue stage. While R1 remains positive, it branches back to the first instruction. That completes the tour, so off we go, starting with cycle 1. Again, we're assuming a nice full instruction fetch queue, so we can always pop an instruction at dispatch. Here we have a new instruction, a load. We have no structural hazards. None of our structures have been allocated, so we can proceed with the dispatch. We allocate a reservation station, copying the opcode. The instruction reads register R1, so we query the map table and find physical register 4, and the ready bit is set. So we copy that tag into the source tag field. But the load also writes to a register. It has created a new value for the register named F0, so we need to allocate a new location for it. Specifically, we need to allocate a new physical register for F0 since we wrote to it. And referring to the free list, let's just take the smallest value there. So we have physical register number 5 is available, which we copy into the output tag field in the reservation station. So hopefully that feels familiar from the Tomasulo example. But what's new here is that we want to achieve precise state, and so we need to remember the old physical register mapped to F0, which was physical register number 1 up here. So that if anything goes wrong, if we have a control miscalculation, if an instruction hits an exception or there's an external interrupt, we have the data to restore the state of the processor to some particular precise point. Now, what structure do we remember this value in? Of course, in the reorder buffer. Hopefully you remember that from the last video. So we remember the old tag in told, and we update the map table so that future readers of F0 know where to find the latest value. So we update it to physical register number 5. And of course, we also track the new physical register tag in the reorder buffer. And last but not least, physical register 5, it has been allocated. So of course we have to remove it from the free list. It now represents the value of F0 as of this load. Okay, we did it. We dispatched this load in cycle 1. So onward to cycle 2. From the instruction fetch queue, we have popped a multiply instruction. Again, we have no structural hazards. We have available physical registers in the free list, available reservation stations, and an available entry in the ROB, so we don't need to stall the dispatch stage. And we start allocating. So the tail pointer has moved downward, representing the latest instruction to be dispatched, or the youngest instruction in the instruction window. We allocate a reservation station entry. The multiply reads F0 and F2, so we copy their current tags into the source register tag fields of this reservation station entry. Along with the ready bits. So only one of the operands is ready. The multiply is waiting for that previous load. The instruction writes to F4, so we need to make a copy of the old tag. And allocate a new location, physical register, for this output. We'll take physical register 6 and update the map table and copy that new output tag into the reorder buffer and the reservation station entry. And now that it's been allocated, we have to remove physical register 6 from the free list. So that's a wrap on the dispatch. But checking in on the issue stage, notice that the load's only input operand has its ready bit set, and so the load in the load 1 field is ready to issue. So we send it to its functional units, querying the data cache and the load store queue in parallel, starting that process in cycle 2. On to cycle 3. So that first load, it is executing. Unlike in the Tomasulo examples from last module, where I showed when an instruction finished the execute stage, as we fill out this pipeline diagram, I'll mark the begin and end cycles in the execute stage. No instruction can currently issue, and so looking to dispatch, we have an instruction to pop from the instruction fetch queue this store. So we move the tail pointer down again, tracking the youngest instruction in the instruction window. And we have ROB and reservation station entries to allocate, so it does not need to stall. I will note that stores are not allocated a physical register since they have no output value. So we allocate a reservation station entry. The store reads registers F4 and R1, so we look up their tags and copy them into the operand tag fields in the reservation station entry, where register R1 is ready, but F4 is not ready. So we will be waiting to find out when this value is ready, looking for a tag match from the CDB. Now, since the store has no output register value, its old and new tags in the reorder buffer don't matter, so that completes dispatch for the store. Onward to cycle 4. The first load is still executing and no instructions can issue, so we look at the dispatch and we've popped a subtract instruction from the instruction fetch queue. We move the tail pointer downward, allocating a reorder buffer entry, and we allocate a reservation station entry for this instruction. It reads register R1, so we copy its tag from the map table into the source operand tag field, which is ready, but it also outputs register R1. So we need to allocate a new physical register, update the map table, and record the old and new tags for register name R1. So we copy the old tag, and allocate a new physical register. So number 7, let's say, update the map table with physical register number 7 and clear the ready bit since the value has not yet been produced. And we copy that tag appropriately into the reorder buffer and the reservation station entry. And that's the dispatch stage for the subtract. On to cycle 5. The load is still executing, the multiply and store have a dependence chain, they can't issue, but the subtract instruction, its operands, there's only one, it's ready, so therefore the subtract instruction can issue. And over in dispatch, we've encountered a branch instruction. So we allocate an ROB entry, moving the tail pointer down. The reservation station for branches are not shown. But we'll assume that there is space since this is the first branch we've encountered. So we're clear to dispatch. We don't need to stall in dispatch. The branch instruction will read R1's value from physical register number 7 when it's ready. When we get a tag match over the CDB. The branch doesn't have an output register, so we don't take anything from the free list. And that's the dispatch for the branch instruction. Onward to cycle 6. The subtract just issued last cycle, so it starts its execute and it finishes in cycle 6. But here's something exciting and different from Tomasulo. The reservation station entry can be freed at the end of the execute stage. So since the subtract has both started and finished its execute, it's a one cycle simple operation in cycle 6, then we can actually deallocate this reservation station entry. Now, why is this? What changed from Tomasulo's algorithm to the R10K? Well, we are not using the reservation station ID as a tag anymore. So remember that in Tomasulo's algorithm, the map table tags could be empty. That signified that the value is ready. Go read it in the architectural register file. But otherwise, a non-empty tag pointed to the reservation station entry holding the instruction that would produce the value. So only at writeback, when the architectural register file would consume the value from the CDB, only then could we free the reservation station entry. But now that we're using a physical register file, we can free these entries one cycle earlier at the end of execution. On this note, I want to correct something that I said in the last video. In the audio track, you probably heard me say that we could free the reservation station entry in the first stage of execute. That doesn't match what I just wrote in cycle 6. Indeed, we need to store the output tag until the end of execute so that we know what value to broadcast on the CDB in the subsequent complete stage. Okay, with that correction out of the way, back to cycle 6. Now, some other excitement happened in cycle 6, which is that the branch was predicted back in the fetch stage as taken. So we dispatch the load instruction from the second loop iteration. Just like with Tomasulo's algorithm, we're now starting to overlap multiple iterations of the loop. Okay, so let's allocate storage for this load, starting with the ROB. So we move the tail pointer down and allocate a reservation station entry. It loads register R1, so we copy that tag into the source operand field number 1, notably not ready. And the interesting part, the load writes to register F0, so we need to make a copy of the old tag and allocate a new physical register, the last of them in the free list, update the map table, copy that new output tag into the reorder buffer and the reservation station entry, and finally remove physical register 8 from the free list if it is not allocatable. And that's it for dispatch of the load instruction. So on to cycle 7. The big news in this cycle is that the subtract completes. So the CDB broadcasts its tag, which is physical register number 7. So we'll assume that in the last cycle, a register close to the CDB was latching the output tag of the subtract instruction, physical register number 7. Now, who is listening to the CDB? The map table and the reservation stations. So these structures both perform an associative lookup. They're looking for a tag match, just like we saw in Tomasulo's algorithm. There's a match in the map table, which sets the ready bit in the map table. So adding that plus symbol there. But we also get a tag match in the reservation station. So we set the ready bit in that second load entry as well. Now, just to clarify that term I used, associative lookup, this means we are indexing or searching a data structure by value in contrast to by position. For example, when we want to look up the current tag of some register name, say F2, we perform direct indexing. We use those bits to indicate which row of the map table to look up and extract the tag number. By contrast, an associative lookup, we don't know which position to search, so we're searching them by value, making comparisons in parallel across all of the rows. This is considerably more expensive in area and energy than a direct lookup, but it's necessary for this design. Another way to think about direct or positional lookups versus associative lookups is to think about an array versus a hash table or a hash set. Okay, so I'll end that tangent there. Coming back to this broadcast of the subtracts tag, again, just a reminder that the value produced by this instruction gets written to the physical register file, and there was notably no value broadcast on the CDB, just the tag. So we're saving quite a bit on wires here. The CDB only broadcasts a few bits now to represent tags in contrast to 32 or even 64 bits for a value. Okay, that wraps up the complete stage for the subtract. None of our instructions have issued for a while, so we don't expect anyone to enter execute. But if we assume that the complete stage updated the ready bits in the first half of the cycle, then by the second half of the cycle, we actually have 2 instructions that we could issue. This load in LD2, its operand is now ready, but additionally the branch instruction that's also reading R1. It's not shown, but its ready bit also would have been set. So this brings us to an interesting question. Can we issue both of these instructions at once? I had been raving about Tomasulo's ability to achieve just that, issuing multiple instructions in the same cycle, but something changed, and that's the fact that to issue, we must now read the physical register values out of the register file and send them to the functional unit. That happens at the issue stage now, in contrast to copying values in the dispatch stage as we did in the last module with Tomasulo's algorithm. Now, register file ports aren't cheap. So if we assume that we only have 2 read ports on the physical register file, that limits how many instructions we can issue in the same cycle. So in this microarchitecture, we will assume only 1 instruction issues per cycle. And that's because the issuing instruction is reading the values out of the register file and into the functional units. So which instruction to issue? That's a loaded question. There are multiple factors to consider here. We might want to issue a younger, long latency operation to get it working faster, possibly reducing the critical path of execution. But we also want older instructions to complete so that they don't hold up resources in the reorder buffer and therefore block the progress of our instruction window. I'm sure that you can find many debates about this in the literature. For now, we'll use a simple heuristic and issue the oldest issuable instruction in the cycle. So that is the branch. It issues in cycle 7. Now, that was a lot of excitement between the completion of the subtract, what instruction do we issue, and we're still not done. The cycle is giving us a lot to learn. Quietly, the dispatch stage peeked into the instruction fetch queue and found this multiply instruction from the second loop iteration. Now remember the first condition that must be checked in the dispatch stage, which is, do we have any structural hazards? Well, there is space in the reorder buffer. We were able to move the tail pointer downward. There is a reservation station entry available, but unfortunately, the multiply instruction stalls in the dispatch stage because there is no available physical register. And this multiply will write to register F4. So I won't mark that the multiply dispatches in cycle 7 because it hasn't yet dispatched. Okay, that wraps up the excitement for cycle 7, onward to cycle 8. So checking in, can we retire any instruction now? Well, the subtract just completed, but the retirement stage checks whether the head instruction has completed. So the subtract is the first instruction that's completed out of order, but we need to retire in order. The load is still executing away on that long latency load that misses the first time. But since the branch instruction just issued, it can now execute. And remember that second load, it's still ready, and we have no contention for the physical register file anymore, so now the load can issue in cycle 8. So it's reading the value in physical register 7, and we're sending this address to the data cache and load store queue in parallel. And checking in on our dispatch stage, has anything changed? No, the multiply is still stalled in dispatch because we have no available physical registers. Onward to cycle 9. Here the branch completes. And since it's an 80 iteration loop, it turns out that prediction of taken, it was correct. So we do not have a misspeculation. I will not yet show you how the recovery process works. This example is all about using these structures in the common case. So the branch completes in cycle 9, nothing else changes. So onward to cycle 10. At long last, the load instruction from the first iteration, it finishes executing. So it was executing from cycle 3 to cycle 10, and that's because we're assuming it was a cache miss, just like in the last module. So it took 8 cycles from begin to end to latch that data. And a quick aside that the details of caches are coming up in the next set of lecture notes in the next module. Since we've reached the end of the execute stage for this load, then we deallocate its reservation station entry. And onward we go to cycle 10. Still nothing has changed for that multiply. Dispatch is stalled. We might be filling that instruction fetch queue now, but onward we go to cycle 11. That first load is in the complete stage, so we're broadcasting its physical register over the CDB, assuming that the CDB latched this tag while the reservation station entry was being deallocated. We perform those associative lookups in the map table where we don't get a tag match on physical register number 5, but over in the reservation station entry we do, and so we set the ready bit for that first multiply instruction, and that wraps up the complete stage for the load instruction. Meanwhile, in the second half of the cycle, at last that first multiply instruction, both of its operands are now ready so it can issue. We send it to the functional units. And last but not least, let's check in on that second load. Apologies, I forgot to mark that it would have started its execution in cycle 9, of course, but the first load still hasn't brought in the cache line, and so even in cycle 10, it's still executing. But finally, in cycle 11, that second load experiences a cache hit, so it only takes one cycle to execute, but that's only after the first load finishes its execute. So that first load, it spent 8 cycles bringing the data into the cache, and only 1 cycle later, that second load finishes up. And again, we'll cover those ideas in the next module on caches. Okay, on to cycle 12. We have some very exciting news in the retire stage. So that first load instruction, it is the oldest active instruction, meaning, of course, it's at the head of the ROB. And it has completed. So at this point, we know it hasn't hit any exception. There was no page fault or permissions problem, and the instruction is certainly not control speculative. It's the oldest active instruction, so it can retire. There is no need to abort and restart the instruction, so the physical register in its old tag, physical register number 1, is returned to the free list. And we deallocate its reorder buffer entry by moving the head pointer downward. We'll see soon for a later dispatch that the tail will then move up to that first entry of the reorder buffer. It's a circular buffer. Okay, what else is happening? Well, the second load finished its execution at the end of cycle 11, so it is now in the complete stage, meaning it latched the tag of its output register, physical register number 8, and that is now broadcasting over the CDB. The value of physical register 8 is of course updated. The functional unit sends the new value to be written to physical register number 8, and we perform these associative lookups looking for tag matches on physical register 8. We find one in the map table here, so we set its ready bit, and there are no tag matches in the reservation stations. Also notice that the first multiply instruction issued last cycle, so it starts executing in this cycle, and making the same assumptions as in our Tomasulo example, this will take 4 cycles from the start of execute to the end. We can't issue any instructions, the store is still waiting on the multiply's output. Now, can we dispatch that second multiply? Although we just added physical register number 1 to the free list, we'll assume that it's not allocatable in this cycle, so the register can be allocated in the next cycle. So onward to cycle 13. At last, in the dispatch stage, we don't have a structural hazard. The second multiply gets the newly freed physical register number 1. So we can proceed with the dispatch. The tail pointer was here already, I'm just going to add it back there. We allocate a reservation station entry. The physical register number 1 is here in the free list as of the end of last cycle. It reads F0 and F2, so we copy their tags into the source operand fields. And of course, the instruction writes to a register R4. That's why it was stalled for so long. So we will update the mapping of register name F4. But first we have to copy the old tag in case we need to abort and recover. And we allocate the one and only free physical register from the free list, recording that in the new tag field, updating the map table, and copying that tag to the reservation station. Finally, removing physical register 1 from the free list. We're back to no allocatable registers. Okay, that's the dispatch of the multiply instruction. Now, the other interesting thing in the cycle is that the head pointer did change due to that retirement in the last cycle. So the first multiply is now the oldest active instruction. It is the oldest instruction in the instruction window, but it has not completed. It's still in the execute stage. So it cannot retire. We have to hold on to that reorder buffer entry, and we can't free the physical register pointed to by its old tag. Okay, that's it for 13, so on to cycle 14. The first multiply, it's still executing. The store is waiting on a value before it can even issue. We have 3 instructions that have completed, but their resources can't be freed. They have to retire in program order. Now, what about the second multiply? Well, both of its ready bits are set, so it can issue in cycle 14. So the multiply number 2 has both operands ready. And checking in on our dispatch stage, at the front of the instruction fetch queue, we have found the store for the second loop iteration. And there's no structural hazard. It can dispatch. In particular, because the store instruction doesn't need a output physical register. So let's dispatch this store. We allocate a new reorder buffer entry, and this is a circular buffer. So the tail wraps around. We allocate the reservation station entry, and it reads register R1 and F4. So we copy their tags, and we were able to proceed despite having an empty free list because the store does not write to any register. So the new and old output tags, it doesn't matter what value's there because this is a store instruction. And that's it for the dispatch of this store from the second loop iteration. On to cycle 15. The first multiply, or the multiply from the first loop iteration, it finishes its execution by the end of cycle 15. So it was executing for 4 cycles The second multiply, it issued last cycle. It read the physical register file last cycle. Don't forget about that. So it starts its execution in cycle 15, and that will run for 4 cycles. There are no other instructions to issue, so turning to dispatch, we can't proceed. There is a structural hazard. Now, what is the structural hazard? Sure, there are no entries in the free list, but hey, maybe the next instruction is a store or a dynamic processor. We don't know. But that's not really the structural hazard. The problem is that there are no more reorder buffer entries. Why is that? Because the tail pointer is right behind the head pointer. It is not possible for us to increment the tail pointer by 1 and allocate that entry to the incoming youngest instruction. We have filled out the instruction window. We're now desperate to retire instructions. So let's see when we get out of this. On to cycle 16. Okay, the first multiply, it is in the complete stage now. And note, I forgot to deallocate the multiply reservation station entry and the last cycle. Now by the end of the execute stage, we latched the output tag of the multiply to be broadcast over the CDB. So we're now broadcasting the output tag of that multiply, and of course writing back the new value to physical register number 6. We have no tag matches in the map table, but we have one here in the reservation station entry, so we set its ready bit. And that is it for the complete stage. But assuming that CDB broadcast and the tag matches happened in the first half of cycle 16, then by the second half, we recognize that both operands in this first store are now ready, and so we can issue. So we read the values from the physical register file for numbers 4 and 6, and send those to be latched at the load store queue. So the store issues in cycle 16. Onward to 17. Looking at the retire stage, the head of the ROB has completed. So in fact, the first multiply instruction, it retires. So we free the physical register from that old tag. We deallocate this reorder buffer entry by advancing the head pointer forward to the next oldest instruction. Our instruction window has advanced by 1 instruction. And since the store issued last cycle, it now executes in cycle 17. But let's be specific about exactly what's happening here. So the store, in fact, finishes its execution. But I really mean that this is only the address computation. We are simply about to latch the store address and value in the load store queue. Crucially, this store does not update memory until it retires. Remember, the goal of this module is out-of-order execution while retaining precise state. We can recover old values of registers because of the told field in the reorder buffer, but we have no means to make a backup of memory, at least in the architecture we've described so far. Talk to me about my research area if you want to hear about undo mechanisms in memory. Okay, and since the store finished its execute, then we also deallocate its reservation station entry here. On to 18. The store just finished execute, so of course it completes in this cycle, but it has no output result, no output value, so it doesn't broadcast, doesn't use the CDB. So its complete stage has little action. The multiply from that second loop iteration, it finished executing its 4 cycles, so we deallocate its reservation station entry. And the other interesting news is, since we retired an instruction just last cycle, then the dispatch stage is free of any structural hazard. We can dispatch this subtract instruction that is at the front of the instruction fetch queue. We have a physical register to allocate, we have a reservation station entry to allocate, and 1 reorder buffer entry is available. So we are good to dispatch the subtract. So we allocate that reorder buffer entry and the reservation station entry. It reads register R1, so we copy that tag to the operand tag field. And of course it writes the same register name R1, so we need to allocate a register. We will update the map table, but first we copy the old register tag, and then the new. And this should say T here. We update the map table to physical register 3, and we clear the ready bit. And physical register 3 is no longer allocatable. The free list is empty, and that is the end of dispatch in cycle 18. Onward to 19. The head of the ROB just completed, so the store instruction retires. There's no register to free here. There's no told value. Now that the store can retire, it's time to update the value in memory. So the head store in the load store queue, it finally writes to memory because the instruction is non-speculative and we haven't detected any page fault or permissions problems. So it's finally safe to commit this value into memory. But that's not the only action in this cycle. Of course, that multiply finished execution last cycle, so now it's in the complete stage. It's broadcasting its output tag over the CDB, and the map table and the reservation stations are looking for tag matches. They're performing those associative lookups, and we get a tag match here, and we set the ready bit, and we also get a match down here in the reservation station entry, so we set its ready bit. We've encountered that interesting predicament in issue stage again. We actually have two instructions with all operands ready, but because the issue stage reads from the register file, we have a finite number of ports. We're going to assume one instruction in issue and only one. So we'll use that heuristic again, picking the oldest issuable instruction. And so the store instruction issues in this cycle onto cycle 20. Checking in on the retire stage. Remember that the head pointer was moved here in the last cycle, and now we see that the head of the RB is complete. So the subtract instruction, it can retire. So we free the physical register from the old tag, and we deallocate that ROB entry, moving the head pointer forward by 1. Now there's no instruction to enter the complete stage, but that store has started and finished its execution, its address computation. Of course, the value isn't written to memory until this store instruction retires, but we can free its reservation station entry since it's finished execution. And over in the issue stage, that subtract instruction at entry number 9, which was sadly overlooked in the last cycle because we can only issue one instruction at a time, well, its operand is ready, so it issues in cycle 20. And finally, recall that the tail pointer was up here. Let's check in on dispatch. There is space for the tail pointer to move down. There are plenty of available reservation station entries, but technically there's no physical register yet latched to be in the free list. Physical register 4 is not yet allocatable. But the good news is the incoming instruction from the fetch queue is a branch, which won't require a new physical register. So we can dispatch. So we move the tail pointer down by 1, and we would allocate an entry in the branch reservation station, not shown. So that's the dispatch of the branch. On to cycle 21. Remember, our head pointer was right here at the branch, and it has completed, so the branch instruction retires. There's no physical register to free, but we deallocate its ROB entry. Notably, let's say that we learned that the branch was predicted correctly. So now we know that all of the instructions until the next branch instruction are not control speculative. We know they've followed the correct control path. The store instruction in entry number 8, it enters the complete stage, but it has nothing to broadcast. The subtract instruction, it starts and finishes its execution since it issued last cycle, so we deallocate its reservation station entry. That second branch instruction is still waiting for the latest value of R1, so it can't issue. But turning to the dispatch stage, remember that our tail pointer was here, and at the front of the instruction fetch queue, we found a load candidate dispatch. Well, we have an entry in the free list, we have an available load reservation station entry, and an available reorder buffer entry. We can dispatch. So we move the tail pointer down, and we allocate the reservation station entry. We copy its input tag, and we need to allocate a new location for name F0. We make a copy of the old tag, allocate the new, and update the map table, and remove it from the free list. And bring it to the reservation station output. And so we've dispatched this load. On to cycle 22. The head of the RB is this load instruction. It's complete, so it can retire. So we deallocate its old tag. Physical register number 5 can be allocated again in a later cycle. We deallocate the reorder buffer entry. That subtract enters the complete stage. So we're broadcasting its output tag over the CDB. And we got a tag match in the map table and in the reservation station. And we would get a tag match in the branch reservation station entry. So yet again, we have found ourselves with 2 issuable instructions. There's a load 1 entry in the load reservation station, but also the branch instruction. But because the issue stage must read the values from the physical register file, and we only have a certain number of ports, we are assuming that only 1 instruction issues per cycle. So we'll issue the branch instruction. Finally, in the dispatch stage, the front of the instruction fetch queue has a multiply instruction for us. Now, can we dispatch? We have a reservation station available. We have a reorder buffer entry available. The tail is here right now, but we assume that we reallocate a freed physical register in the following cycle. So in fact, we do not dispatch the multiply yet. It is stalled in dispatch. So on to cycle 23. The head instruction was here. It's complete, so the multiply retires, meaning we can deallocate its old tag physical register and deallocate the reorder buffer entry. No instruction is completing, but the branch is now executing and finishing its execute. So if we can see its reservation station entry, we would deallocate that now as well. This load instruction is ready to dispatch. Its operands were ready last time, and now we get our chance to issue it because it can read from the physical register file. There's not a structural hazard on the physical register file this cycle. And revisiting that dispatch, yes, we can dispatch the multiply now. So we allocate the reorder buffer entry, we allocate a reservation station entry, and we copy the tags for register names F0 and F2, where F0 is not yet ready, but F2 is ready. And the multiply writes F4, so we need to allocate a new physical register, but not before we copy the old tag. And we'll allocate physical register number 5 and update the map table and copy this output tag to the reservation station. And that is it. We've done the dispatch. On to 24. Our head pointer was here. The head of the reorder buffer is complete, so the store retires. We deallocate the reorder buffer entry. The branch instruction completes, but has no output, so it doesn't broadcast. The load instruction from the third iteration starts and finishes its execute in cycle 24 because it gets a cache hit, assuming we exploit spatial locality, which we'll see in more detail in the module on caches. So we deallocate its reservation station entry. There's no instruction to issue, and looking at dispatch, we've popped a store instruction from the instruction fetch queue, and we have no structural hazards, so it's time to dispatch the store, allocating its reservation station entry. And the store doesn't write any register, so we don't need to allocate a physical register. And that's it for dispatch. Cycle 25. We can retire yet another instruction, the subtract. It has completed. So we free its physical register in the old tag and deallocate its reorder buffer entry. The load instruction is entering the complete stage, so it is broadcasting its output tag on the CDB. The value is written directly to physical register number 4, and we find a tag match in the map table and the reservation station. So that's the complete stage of the load instruction in the first half of cycle 25. And in the second half, in the issue stage, we see that the mult1 instruction is ready to issue. Both of its operands are ready. So it can now issue in the second half of cycle 25. And finally, in dispatch, we found a subtract instruction from the instruction fetch queue. We can dispatch. So there's our ROB entry. Let's allocate that reservation station entry. And since this instruction writing to register R1, so we need to make a copy of its old tag and allocate a new output, a new location, which will be physical register 6. 7 technically isn't even ready yet. And so we update the map table with this new location for register R1. We remove number 6 from the free list, and that is it for dispatch. And that brings us to our last cycle, cycle 26, where we are about to dispatch our last instruction for 3 loop iterations. But first, let's go in order backward through our stages. The head pointer was here at the branch instruction. It's complete, so we can retire the branch instruction, which means that officially 2 iterations of the loop have finished. They have dispatched in order and retired in order by cycle 26. The multiply instruction issued last cycle, so it starts its execution now, and it will run for 4 more cycles. Now looking at the issue stage, technically this should have physical register number 5 already. So the store can't issue, we're still waiting on that value. But the subtract that dispatched last cycle, its operand is ready, so it can issue in the cycle. And last but not least, looking at the dispatch stage, our tail pointer was here. At the front of the instruction fetch queue is the branch instruction from the 3rd loop iteration. Now, can it dispatch? Well, we'll assume that there's an available reservation station entry, it doesn't need a physical register, and we have a reorder buffer entry, so yes, it can dispatch in the cycle. We allocate that entry and dispatch. Great. So I hope that this example actually illustrated how we use these different structures, how the instructions move from dispatch to issue to execute to complete to retirement, and that you're comfortable with the MIPS R10K out of order design. So let's just summarize what we observed in this example. So one key takeaway from this example is the difference between completion and retirement. Of course, we've witnessed out of order execution. That's what we started with in Module 4, and we've retained out of order completion, where we update the physical register file with values as soon as they become available. Just like with Tomasulo, we're building up a dynamic data flow graph and executing instructions as soon as they can. So this column shows us that the complete cycles are out of order with respect to program order, but out of order right back to the architectural state of the processor is what prevented us from keeping precise state. But now we've seen in order retirement. The cycle at which instructions retire increases monotonically in program order. Now I want to note a couple of performance degradations here. The delay in completion from this load to this multiply, this was largely due to the long latency read after write dependence, that 8-cycle cache miss. But we were able to fill the pipeline with other useful work. This is the purpose of out-of-order execution. We were able to hide that penalty. But in contrast, we had a significant delay between this load and that multiply. This was only a 1-cycle read after write dependence, yet between cycle 12 and 19, there wasn't as much useful activity in the pipeline. So performance suffered here. Not because of the single cycle read after write dependence, but instead because there were not enough physical registers. If you revisit the storyline, if you go look through the slides, you'll see that that multiply was stalled in dispatch for 7 cycles simply because we ran out of physical registers. So this example illustrates how important it is to properly size these different resources on chip. It's a tricky balance between maintaining a high average instruction throughput while ensuring that the resources are well utilized. Otherwise, we should dedicate those transistors to some other purpose to improve performance in another way. These are the kinds of really interesting design trade-offs that computer architects need to make. Now, after all of this example, you might be wondering, how does all of this help with exceptions? I.e., what have we been striving for toward this so-called precise state? Well, I'm going to pause this video here, and we're going to discuss that in the next video. Exactly how do we maintain precise state in the R10K, reconsidering our example briefly, with an exception caused by one of the instructions in our program that we saw in this video. We're going to see recovery in action, so I will see you there.